Hello, everyone. Let me walk you through this week's highlights on modern physics. So, I want to start by talking about light. So, light is an electromagnetic wave. And we've already talked about how a changing electric field can generate a magnetic field. That's just an electromagnet that we worked on before. But what we haven't talked about was that a changing magnetic field can also generate an electric field. So, what's happening here is by having a changing electric field that generates a changing magnetic field, which generates a changing electric field, and back and forth it goes. And that is what light is. Light is an electromagnetic wave where both of these fields are kind of propagating and changing and becoming each other. With that idea, I want to talk about something called black body radiation. Now, that is just when objects get hot, they emit light. We've seen this. Here's a picture of hot coals here. Now, when we do an experiment and we measure how bright the light that's coming out for each of the colors of that light, we get a plot like this where this vertical axis, this is the intensity of the light that's being emitted, and the horizontal axis, this is the colors or the wavelength of the light that's being emitted. Okay. Now, when we do this measurement, we notice that there's hardly any ultraviolet light, and that's great because ultraviolet light is not great for our skin. But it's a problem when we apply this idea that light is an electromagnetic wave. When we apply that to black body radiation, we get a lot of ultraviolet light being emitted. So what they did was is they discovered that, well, if you say that light comes in tiny little packets of light rather than kind of a continuous spectrum of energy, that it solves this problem and the math will match what our experimental values show. Now, this is called quantization. That light is quantized, and each packet of light is called a photon. So the energy of each of these individual photons is equal to h, which is Planck's constant, times f, which is the frequency of that light, the frequency of the photon. And Planck's constant is just this constant, 6.6 times 10 to the negative 34th joules. So for a particular frequency or color of light, if I wanted to ask, like, what's the smallest energy that light could have, we could plug it into this equation, and that will tell us. Now, the next lowest energy would be two of these, right? Because it's quantized. You can't have one and a half of a photon. So you have one, two, three, and so on. So light's going to come in these individual packets. So let's say I want to know green light has a wavelength of 530 nanometers. What's the energy of one photon of green light? Well, this is the wavelength of green light, but we need the frequency of green light in order to calculate this energy. So we need to go back and remember our relationship between velocity, wavelength, and frequency. So V equals lambda f. Now for light, we know that the speed of light is 3 times 10 to the 8th meters per second. So we can plug that in and solve for frequency, and we arrive at a frequency of 5.66 times 10 to the 14th hertz. So now that we have the frequency of light, we can plug it into our energy equation here to calculate what the energy of one photon of green light is going to be. So E equals hf, and we plug in our values, Planck's constant here, and then the frequency we calculated, and we arrive at this value for the energy of one photon of light, green light, 3.74 times 10 to the negative 19th joules. Another interesting property of light is that it has momentum. So here's an image I pulled from your textbook where this is a comet that is going around the sun. Now, this comet is leaving a trail directly behind it. Well, not directly behind it, but directly away from the sun. So when the light from the sun hits the comet, it kind of blasts some of the particles off. And then those are pushed in a way where you're left with a trail pointing directly away from the sun. And so this is some strong evidence that light has momentum to it. So when it collides with these particles, that actually pushes the particles in a particular direction. And so we have an equation for the momentum of light, where P, the momentum of a photon, is equal to h, Planck's constant again, divided by the wavelength of this photon of light. So here's Planck's constant here. So let's calculate. What is the momentum of an X-ray with a wavelength of 5 nanometers? Well, we know that P equals h over lambda. So we plug in those values, Planck's constant and the wavelength of our light, 5 nanometers, 5 times 10 to the negative 9th. And we arrive at this value, 1.32 times 10 to the negative 25th is the value for the momentum of an X-ray of light, of this wavelength. All right, let's talk about the wave-particle duality of nature. If you haven't already watched the Dr. Quantum video that I posted, please pause this and go ahead and watch that now. But here I have waves that are traveling into two small slits. Now, when they go through these slits, they're going to interfere with each other to give you this interference pattern on the other side. Well, as we know, this same thing happens when we use this with particles. So there is some wave properties to particles. So these apply just to both the particles and to waves at the same time. And there's a particular equation that we can use to calculate what the wavelength of these particles is going to be, and that's called the de Broglie wavelength. So that's this equation here, where lambda, this is the wavelength of a particle, h is Planck's constant again, and p is the momentum of the particle. So let's say a baseball is thrown at 100 miles an hour, so it has a momentum of 6.48. I want to know what's the wavelength of this baseball going to be. Well, we can plug that in, lambda equals h over p. We plug in the values that I told you, and we arrive at a wavelength of 2.02 times 10 to the negative 34th meters as the wavelength of this baseball. Here I have a wave on a string. And so you can imagine I have this flat string, and I just take it and I move it up and down until I generate a pattern that looks like this as it moves along the string. My question is, like, where is it? What is its position? You're probably going to say, well, somewhere right here, right? This would be the center position of this wave, right? But, it has some kind of bounds to it. So it could be, it's in between kind of here and here. It turns out that this space here is approximately the wavelength of a particle. And so the position is some kind of x position, some kind of center position, plus or minus its wavelength. And so this is what's called the Heisenberg uncertainty principle, where the uncertainty, or kind of the range that a particle could be in, is approximately the wavelength of that particle. So let's go back to that baseball example. Well, here, right, this uncertainty position is the wavelength of the particle. So back to the baseball, we know that it has a wavelength of 2.02 times 10 to the negative 34th meters. What's the uncertainty, the intrinsic uncertainty of its position? Well, it's going to be the same value, isn't it? So it has an intrinsic uncertainty in its position of 2.02 times 10 to the negative 34th meters. Well, this is so tiny. So as you were to observe this from the stands, this baseball, moving at 100 miles an hour, its uncertainty is so small that you can almost just say it doesn't have an intrinsic uncertainty at all. Now, there's always an uncertainty in measurements, right? Like if you were to watch a video of this and try to determine which position, there's uncertainty there. But this is the intrinsic uncertainty. You can't get any lower than this due to the wave nature of particles. This also is true for momentum. There's an intrinsic uncertainty in the momentum of a particle due to the wave nature of particles. So this is approximately h over lambda. So we got Planck's constant again. This lambda, of course, is the wavelength of the particle. Now we can multiply these two things together, right? The uncertainty in position multiplied by the uncertainty in momentum. And you'll notice that the wavelength cancels out. So if we want to measure the uncertainty in position and the uncertainty in momentum at the same time, we multiply those two uncertainties together, and it's approximately h, which is Planck's constant. Now, Heisenberg did a lot of experiments and calculations to determine what is the smallest value that this uncertainty could be. So this is I can approximate, like it's approximately this. But with a perfect ideal setup, the smallest that it could be is h over 4 pi. So this is the intrinsic uncertainty in simultaneously measuring the uncertainty in position and the uncertainty in momentum is h over 4 pi. Now, this is due to the wave property of particles or objects. All right, this is the same part of before, but here is the question I want to go over. So let's say the momentum of an electron is measured, and the uncertainty in that measurement is 2 times 10 to the negative 33. So this is the uncertainty in the momentum of that electron. What's the smallest possible value for the uncertainty in the position of the electron at this time? So remember, simultaneous, so at the same time. So the uncertainty could be bigger than h over 4 pi, but if we want to know the smallest possible uncertainty, we're going to make that turn that into an equal sign, so that the smallest is when this is at equals to each other. So I want to know the uncertainty in position, so I can just divide the uncertainty in momentum to both sides, and then I can plug in my numbers. So I plug in h, and I plug in my uncertainty in momentum, and I arrive at a value that the smallest uncertainty in the position of this electron is 0.026 meters. So it's not possible to get it any smaller because an electron has wave properties. All right, here is the summary slide with all the equations on it. I hope this helps. Let's get started.